Hi everybody, this is lesson 6.4, comparing linear and nonlinear functions. So your goal is to understand how to identify linear versus nonlinear functions depending on which way we represent them, as graphs, as equations, as tables, and so forth. Alright, so I think what we best want to do here is start off with a real world example. Well, maybe not real world, but a geometry example. Let's say we're taking a look at this problem. We're looking at rectangles. And in this case, we've got all these similar rectangles, and one side's labeled x and one side's labeled 2x, which just basically means that all the rectangles, no matter what size they are twice as wide as they are high. And so let's say I want to take a look at that as a function. Well, it might look something like this. The perimeter would just be the shorter side x plus 2x plus the third side x plus the fourth side 2x, which would simplify down to perimeter equaling 6 times x, depending on what x is and which size rectangle we're looking at. Alright, so if I were to make this function into a table, it would look something like this, where I take x, plug in 1, 6 times 1, I would get 6. If I go to the next larger rectangle and I go x is 2, 6 times 2 is 12, and if I keep repeating that, I get 3 is 18, 4 is 24, and 5 is 30. And so what we get would be a graph that would look like this. So starting at 0, 0, because if we're starting with, even before this one, a size 0, x is 0, well then the perimeter is going to be 0. But when x is 1, perimeter is 6, x is 2, perimeter is 12, 3, it's 18, so on and so forth, and we get this graph. And so trying to identify whether or not this was a linear or nonlinear function, well, as an equation, wasn't quite sure. As a table, I wasn't quite sure. But as a graph, I can tell by the graph that this is a linear function, because linear functions are defined by the fact that they create straight line graphs. And so our goal today is to be able to do that, to be able to see, oh, well, as a graph, this is a linear function. But as a table, what about this tells us that it's a linear function? And what about this equation tells us it's a linear function? Let's take a look at the same scenario, but let's talk about area. What if I had the same rectangles, but then I were doing area? Well, area is base times height, so here I've got area equaling the base, which was 2x, times the height, which is x, and if I simplify that, I get the area equals 2x squared. Well, it turns out if I start doing the same thing, x is 1, plug it in, 1 squared is 1 times 2 is 2. Take the 2, plug it in. 2 squared is 4 times 2 is 8. And don't forget what I'm doing here. Exponents comes before multiplication, so I have to square the number first, then multiply by 2. All right, x is 3. 3 squared is 9. 9 times 2 is 18. I keep going. 4, I'll get 32. And 5, I'll get 50. When I go to graph those, at those key locations, you'll notice I get more of a curve. Okay, a nonlinear function. Okay, anything that doesn't create a straight line with the same slope throughout is nonlinear. Okay, and as a graph, it's obvious. But as a table, we have to figure out what was the giveaway. How could I tell from a table that this would be nonlinear? Or from the equation? All right, so that's what we're going to work on today. All right, so as far as graphs, how do you identify linear versus nonlinear? It's like we were just saying, linear has to be a straight line. Or another way to think about it is the slope is consistently the same throughout. Okay, and it's this idea of slope that's going to help us. Like this one, no matter where I look on here, I have a slope of 0. Over here, over here, over here. The slope is consistently 0 throughout the entire line. But if I look at this one, which is obviously nonlinear, here if I look at the slope is 0. But then here, looks like the slope goes up to 1. As the line gets steeper, the slope increases. This might be a slope of 3 or 4. If I go down this way, this looks like also a slope of 1, Down here, a more steep slope like 3 or 4. But the important thing is on this nonlinear function that the slope changes constantly as I move from place to place. Whereas on a linear graph, the slope is the same throughout because it's supposed to be a straight line. Okay, this is going to actually help us identify linear versus nonlinear in the other examples.